Okay, so let's start today's lecture. Okay, so now previously we have been talking about like the homogeneous system of equations, right? So homogeneous linear systems. So that means that the equation is x prime is equal to something like a of x, right? So like if you want to have an initial condition, then you can put an initial condition there. That will be the full problem that you are going to work with. Okay, so here in the last part of these lectures, we're going to talk about non-homogeneous equations. Okay, so non-homogeneous equations, right? So for the non-homogeneous equations, these equations are going to look like x prime is equal to ax plus g of t is a vector, where x of 0 is going to be equal to x0, right? So that's going to what we're going to call it the non-homogeneous equations. Okay, non-homogeneous equation. So we're going to kind of try to solve such non-homogeneous equations, in particular, in the case when the matrix A is 2 by 2, right? So let's say matrix A is equal to A, B, C, D. Okay, so we want to solve this non-homogeneous. Now remember, the whole theory here, okay, so the whole theory here is in parallel to this kind of homogeneous equation. Okay, so let's say homogeneous equation, right? So homogeneous equation, which is like the A, okay, so let's say second order homogeneous equations, AY double prime plus BY prime plus CY is equal to 0, right? So that's a homogeneous equation. And if you want to consider the non-homogeneous equation, right? So if you want to consider non-homogeneous equation, then it must look like AY double prime plus BY prime plus CY is equal to the right-hand side is G of T, right? So if you study the homogeneous, non-homogeneous equations, there are two ways to solve it, right? So the first is called the method of undetermined coefficients, right? So if you still remember, it kind of depends on the G of T is equal to like e power alpha T, or maybe sine, cosine, right? So cosine beta T and sine beta T. So this is just a little bit of the review, right? So, or it might be polynomial. Then you're going to try method of undetermined coefficients. The other method is called the variation of parameters, right? So what's the variation of parameter? Variation of parameter simply says that you first solve the homogeneous equation. What is the solution to this homogeneous equation? Well, solution to the homogeneous equation is C1 y1 of t plus the C2 y2 of t. There are two fundamental solutions. And the variation of parameters basically says that you can try a particular solution of u1t of y1 of t plus u2t of y2 of t, right? So you can try this particular solution. In particular, you are able to solve for u1, u2 if you have the g of t and the so-called variational parameter formula. Is that good for everybody? Okay, so that's kind of what we've been talking about before. And now we are going to do the same thing for the system of equations. So we're going to talk about the method of undetermined coefficients and the method of variational parameters. Okay, so today we're going to kind of force the focus on the variational parameters. Okay, so the order is a little bit different from what we did before, because previously we first do method of undetermined coefficients before we do variational parameters. So here we're going to do variational parameters first, and then we're going to talk in our next lecture about the method of undetermined coefficients. Okay, so that's our plan. So this is kind of the story for the whole problem, right? So that's in order to do variational parameters, we are going to kind of try to kind of work through this whole non-homogeneous system, right? So that means that if you give me the non-homogeneous system, let's say x prime of t is equal to pt x of t, right, plus g of t. In particular, p can be the matrix A, right? So let's say it can be the matrix A, right? So then you're going to first solve the so-called complementary equation, right? So complementary equation, right? So what will be the complementary equation? Well, as before, complementary equation is kind of removing the G of T, right? So whenever you are removing the non-homogeneous term, the equation that you obtain is called the complementary equation. Is that good for everybody? Okay, so once you have the complementary equation is going to have solutions, right? So what is the solution to this complementary equation? Well, complementary equation is going to have solutions that looks like x of t is equal to c1 x1 of t, right? So plus dot 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 plus cn xn of t. This c1 up to cn is what we call it the coefficients, and x1 up to xn so-called fundamental solutions, right? So let's say linear combination. Okay, so linear combination of fundamental solutions. Right, so this kind of thing is exactly parallel to the higher order equations, but it's everything is a matrix form. In particular, last lecture we've been talking about the matrix. Because psi of t is like you put all these fundamental solutions as column vectors in a row, you're going to reach a square matrix. This is the so-called fundamental matrix. Right, so that's what we call it the fundamental matrix. So that's kind of how you pass from the fundamental solutions to the fundamental matrix. Okay, so this is what we call fundamental matrix. So we talked about it last time. Now, once you have the complementary equation, you're going to consider the particular solution. Right, so you consider one particular solution. That means capital X, right? So prime of t is just the particular solution of the non-homogeneous system. So that means x prime of t is equal to ptxt plus g of t. So then you're going to say that the general solution, right? So let's say the general solution is going to be given by x of t is equal to xc, the complementary solution, plus the particular solution. That's what you're going to have. The good fabric, right? So that's kind of the panoramic picture of the major steps, how you find a solution to non-homogeneous system. So that's the point here is how do you find the particular solution, right? So the point here is how do you find the particular solution. So the particular solution, as we just record at the beginning of this lecture, in a series of second order equations, if you start from a non-homogeneous second order equation, you first work with the complementary equation, and once you have the complementary equation, the complementary solution are linear combinations of the fundamental solutions, right? So, but then you're going to find the particular solution to the non-homogeneous equation by the method of variation of parameters, which means that you're going to vary the parameter c1 into a function u1 of t, and the parameter u2 c2 into a function u2 of t, right? So if you still remember, right? So, and in particular, there is a nice formula for u1 u2, namely the u1, right? So is so minus y1, so minus y2 plus y1. You must remember this. So that means minus the y2 multiplied by the right hand side divided by the Wronskian of y1 y2, and that's integrated. And u2 is equal to the integral of plus y1 multiplied by the right hand side divided by the Wronskian between y1 and y2. That's what our formula we talked about, right? So in particular, this coefficient g must correspond to this equation, which must be in standard form. So the coefficient here must be 1 in order to have standard form, and the W is the Wronskian between the two fundamental solutions. The only thing you have to memorize is this minus y2 and plus y1. So that's because this time we have to gradually do some review of what's happening in this lecture. So that's kind of a brief review of what's happening here. Okay, so that's kind of a brief review of what's happening here. So that's the variational parameters. Now, can we do the same thing for the variational parameters in this here? Well, the answer is yes. Okay, so the answer is yes. So that what happened here is that let's look at this complementary solution. Okay, so let's say the complementary solution, right? So the complementary solution is going to take the form xc of t is equal to c1 x1 of t plus dot 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 plus cn xn of t, right? So x1 and x up to xn are the so-called fundamental solutions, right? So and c1 up to cn are the coefficients. Okay, so this is the complementary solution. Now we're going to kind of rewrite the complementary solution using the complementary matrix. Okay, so so using the fundamental matrix. Okay, so the fundamental matrix, remember, is going to put those fundamental solutions for the complementary equation as a column vectors in a row. So that kind of thing is going to tell you that we can write everything like this: x1 of t dot 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 up to xn of t, and then you're going to multiply by the coefficient c1 up to cn. So as long as you have this, sometimes some people are going to kind of question. It looks like this is a row vector multiplied by a column vector. So what's the rationale behind doing this, right? So what's the rationale behind this business? Well, it's kind of very simple. You're going to kind of treat this row vector, this matrix, as a row vector where each component of this row vector is a column vector. So that's a vector of vectors, which we talked about before. So you can just think of this as x1 up to xn. This is the vector multiplied by c1 up to cn. This is going to x1 c1 plus dot 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 plus x and cn. But here you're going to replace the x's by vectors so that you're going to reach the combinations, linear combinations. So that's kind of the art of using matrices. It can sometimes make the calculation much more simpler, right? So if you kind of use these matrices. Is that good for everybody? Okay, so that's the kind of what we have here. Now we're going to write this very simply as the fundamental matrix multiplied by the vector c, where the vector c is introduced as c1 up to cn. Okay, so that's the vector c is introduced as c1 up to c. So that's going to be what we call a complementary solution. Okay, so that's going to be what we call a complementary solution, right? So now you're going to kind of look at the particular solution. Okay, so let's say the particular solution by the method of variational parameters, right? So we're going to kind of look at the particular solution by the method of variational parameters, which means that you're going to say that x of t, you variate the parameters. So that's u1 of t multiplied by x1 of t plus dot 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 plus un of t, right? So multiply by xn of t. So that must be the variation of parameters. Tells you that you variate this constant c1 up to cn into the functions u1 up to un. Is that good for everybody? Okay, so that's what we're going to call variational parameters. So this one can actually be written as psi of t multiplied by a vector u of t, where the vector u of t is equal to u1 of t up to un of t, right? So this is going to be a vector, right? So this is going to be a vector u1 of t up to un of t. So that's going to be the particular solution by variational parameters. So therefore, once you have this form of the variational parameters solutions, then you're going to say that because this new solution, that particular solution, must satisfy the original equation. So that's xt is pt plus the g of t. It must satisfy this equation. So it suffices to calculate x prime of t. Remember, we have been saying that the x of t is equal to the fundamental matrix multiplied by this variation of parameters u of t. So therefore, if you calculate x prime of t, it is going to be equal to psi of t multiplied by u of t. Okay, so psi of t multiplied by u of t prime. So how do we calculate this, right? So this looks like very strange. It is a matrix that multiplied by a vector. You take a derivative. Now I claim that this is the same thing as like, let's say, the product rule, which means that you can formally apply the product rule, which means this is psi prime u plus psi of t multiplied by u prime of t. Okay, so that's going to be the case. Now, some people is going to say, well, this is just the formal. How are you going to pass it over? Well, you can see that this one is nothing but u1 of t multiplied by the solution x1 of t plus dot 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 plus un of t multiplied by the fundamental solution xn of t. If you take a derivative of that, then you can see that each term is going to be represented as u1 prime of t, right? So let's say a summation in I, ui prime of t, xi of t plus ui of t multiplied by xi prime of t. You sum this whole object, and I leave to you as an exercise to double check that this is nothing but what we have here. Okay, so this is going to be only a side remark that helps you, that asks you to check that this is indeed true. Okay, so that's kind of, I will leave to you as just a homework exercise, which I'm going to bracket here. Okay, so that's only a homework exercise. So therefore, you're going to have this relation. Now, the only thing then you're interested in, what is the Kasai prime of t? The good fabric, right? So remember, the Kasai of t is just an abbreviation of the fundamental matrix. The actual fundamental matrix are the column vectors put in a row, right? So x1, xn, they're fundamental solutions. You put them as column vectors in a row. Then you can see that Kasai prime of t is just term-wise derivative. So x1 prime of t dot 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 xn prime of t, right? So you're going to have something like this. Is that good for everybody? Now, once you have something like this, remember these are the so-called fundamental solution. So what does it mean, a fundamental solution? Fundamental solution, it means that for each xi, right? So for each xi, you're going to have xi prime of t is equal to pt multiplied by xi of t, right? So no matter which I you take, xi prime of t is equal to pt xi of t, because there must be solutions to this so-called complementary equation, right? So here I have emphasized that when we talk about the fundamental solutions, they're fundamental solutions of the complementary equation. So that being said, it means that this one is going to be equal to pt of x1 of t, right? So the first solution until you reach the nth solution is pt xn of t. You're going to reach all these solutions. So this one can actually be abbreviated as the matrix p of t, right? So multiplied by x1 of t dot 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 up to xn of t. So I just factor p of t out, right? So, and this is nothing but the p of t multiplied by psi of t itself. The good fabric, right? So you get very simple and very simple formula that this is just the pt psi t. So that's the psi prime of t. So if you kind of work through this equation, you're going to see that what we already have here is just saying that x prime of t is equal to, so the psi prime is pt psi t. So that means you're going to use the pt psi t multiplied by u of t, right? So psi t multiplied by u of t plus the psi of t multiplied by u prime of t. Is that good, family? Okay, so that's x prime of t, and we just would like x prime of t to be equal to ptxt plus gt, right? So that's what we want to have, pt of the xt plus the gt. So that's our goal, right? So this x prime of t is the particular solution that you're looking for the non-homogeneous equation. So it must satisfy this equation. Is that good, family? But the x of t was supposed to be psi t ut, right? So that's a variation of parameters, psi t ut. So that means this psi t ut is nothing but the x of t. And therefore, this term and this term, they're just equal and they just get cancelled. So finally, what you get, okay? So finally, what you get is saying that psi t u prime of t is equal to g of t. So that's going to be saying that u prime of t is equal to psi inverse of t multiplied by g of t. Is that good, family? Okay, so that's going to be kind of telling you that u prime is solved. So basically, you get ut is the integral of psi inverse of t multiplied by the g of t, then plus, let's say, some constants. So let me say a constant vector u. Is that good for everybody? Okay, so if you use that u of t into the particular solution, so let's say the particular solution, right? So if you use that u of t into the particular solution, it's going to tell you that x of t is equal to cosine of t, right? So let's say cosine of t multiplied by u of t. So that's going to kind of tell you that this is going to have the solution cosine of t of the integral cosine inverse of t multiplied by g of t plus cosine of t multiplied by the vector u. Is that good, right? So, however, you can see that the vector u is nothing but a constant vector, right? So let's say it is a vector c. And if you have cosine t of c, it is nothing but one of the complementary solutions. Is that good, family? Remember, we are going to just look for one particular solution. We don't worry about any kind of additional complementary solutions because they are not going to alter this equation, right? So the complementary solution is always the solution to the homogeneous equation, and adding or subtracting any kind of proportion to the any complementary solution, it won't quite hurt our choice of just one particular solution. We remember we don't need so many particular solutions. We just need one particular solution. Is that good, family? Okay, so once you have that, it means that you really don't need this term, right? So you really don't need this term. So finally, let us summarize our result. Okay, so right, so summary is that we're going to talk about the variational parameters for the non-homogeneous equation. So that means x prime of t is given by a non-homogeneous equation ptxt plus the g of t. So that's the non-homogeneous equation that we're interested in. Now, what happened here is that first you're going to kind of look for, okay, so let's say first step, you're going to look for x prime c of t complementary solution is equal to pt xc of t. That's complementary solution. And the solution is given by xc of t is equal to the fundamental matrix multiplied by c, where the fundamental matrix is going to be given by the fundamental solutions. You put all these fundamental solutions as column vectors in a row. That's going to be the fundamental matrix. Okay, so that's the first step. Now, once you have the first step, you are going to kind of work with the second step is the variational parameters. So that means you're going to set a particular solution to be x. Okay, so to be the particular solution to be equal to the fundamental matrix multiplied by u of t. But then you're going to tell me that the u of t has a solution which is integral, okay, so of cosine inverse of t multiplied by the right-hand side vector of the dt. That's going to be the integral. Is that good for everybody? Okay, so that's going to tell you that you're going to calculate the inverse. Sorry, so this is not the inverse. Okay, so here, okay, so it is inverse, right? So yes, so you're going to have this, right? So that means you have to calculate the inverse matrix of this fundamental matrix, and then you can multiply it by the right-hand side. So this is a matrix multiplied by vector integrated. So if you combine these two formulas, it's going to tell you that the particular solution takes the form of cosine t of the integral of cosine inverse of t multiplied by g of t dt, right? So that's going to be kind of the particular solution. So finally, we reach the formula. Okay, so the general solution. Okay, so the general solution has such a nice formula that the general solution x of t, if you combine these two parts, it is going to be equal to cosine t multiplied by c plus the cosine t multiplied by the integral cosine inverse of t multiplied by g of t dt. Right, so that's going to be kind of what happens to this general solution. That's going to give you such an equation. Is that good for everybody? Okay, so that's kind of the general solution to the non-homogeneous problem. Okay, so this is going to be a super important formula that you must know how to implement it in practice. Okay, so remember, in order to solve for such non-homogeneous system, I just needed to find the fundamental matrix for the corresponding homogeneous system. Once you have the fundamental matrix, all the information are incorporated into the fundamental matrix, as well as the non-homogeneous term. You just have to kind of calculate, right? So just have to kind of calculate cosine t multiplied by constant and cosine t integration of cosine inverse of t multiplied by the right hand side. So that's what you're going to do for this type of problem. Okay. So now this formula is going to be kind of very important. So let's look at this formula carefully. Okay. So it says that the general solution is equal to the cosine t multiplied by c multiplied by let's say added by cosine t of the integral of cosine inverse of t multiplied by g of t dt. So that's going to be the formula. So some people is going to say, well, here is the cosine t, there's a cosine inverse of t. Maybe this product cancel, so that let's say we're going to kind of equal to the integral of the g of t dt, right? So that's some people is going to say, well, there's I don't have to do anything, but this is wrong. Okay, so this is wrong. So why it is wrong? So that's going to be a nice question. Why it is wrong? Well, if it is wrong, you have to look back into what's happening in this, right? So you have to kind of look back into what happened into our calculation. Remember, here this just says that u prime of t is equal to cosine t inverse of t multiplied by g of t. So when you integrate, indeed, what happens here is that this integration is corresponding to something like from t0 to t of the s of the ds. Is that good, family? Okay, so that exact t is not happening there. Okay, so but rather it is replaced by s to be accurate. Here, the reason why I don't want that s is because I already have a variation of constants. I mean, I already have the indefinite integral. I have a constant here. But if you take into account, the actually, okay, so actually, we should say that the x of t is equal to what? Well, it is equal to some cosine t multiplied by c plus cosine t multiplied by the integration up to t of the cosine inverse of s multiplied by g of s ds. So to be more exact, it is an integration like this. Some people is going to ask why you don't start from anywhere. Well, you can start from anywhere you like, because here you start from t0, but if I start from a t0 theta, you can double check that you are going to end up with just another constant. So, but the constant is arbitrary because they're just the line in the complementary. That's why we never wrote the starting point of the integral, but we just write things like this. So that'll be more precise. So this t agrees with the upper integration bound for the t, and inside the integral, you're integrating something like s, right? So this formula is not exactly right, but it's useful because you can just calculate the integral first. You're going to end up with some antiderivative in terms of t, and then multiply by cosine of t. You just have to bear in mind that what actually happens is that the integration is with respect to another dummy variable. So these are called dummy variable, another dummy variable s, and you integrate up to t, right? So, but it doesn't quite matter because in any case, you're just finding an antiderivative. Is that good, family? Okay, so let's say we will just kind of work with this formula. You're just calculating antiderivative. Once you have the antiderivative, you have everything. Is that good, family? Okay, so that's the first remark. Now, the second remark I would like to make is about this problem, is that here you have to calculate the inverse matrix. So what happens in practice on an exam is that your equation is going to look like x prime of t is equal to a x of t plus some right-hand side, where the matrix A is a 2 by 2 matrix, A, B, C, D. So in that case, the cosine of t is going to be a 2 by 2 matrix, right? So let's say x11 of t, x12 of t, x21 of t, right? So, so that's not going to be the case. Okay, so x12, x21 of t, x22 of t. So that's going to be what happens here. And if you have that matrix, remember the inverse matrix, we've been talking about this inverse matrix. It is 1 over the determinant of cosine. You switch the diagonal, you take a negative on the off diagonal. So that means x22 of t, x11 of t, you take a negative x minus x12 of t minus x21 of t. Take a negative on the off diagonal. Is that good for everybody? Okay, so that's how you calculate the inverse of 2 by 2 matrices, which is very important. And the third thing I would like to remark is that once you have the inverse matrix, you have to use this 2 by 2 matrix multiplied by a vector. So what happens here is that you're going to use the vector matrix product, right? So matrix product. So that means you're going to have a matrix. So let's say A, okay, so A, B, C, D, right? So let's say, let me use Greek letters, okay? So that means you're going to have alpha, beta, gamma, and delta, right? So this matrix multiplied by vector, okay, G1 and G2. So that matrix vector product is going to just give you a matrix, a vector, a alpha G1 plus beta of G2, and let's say gamma G1 plus delta of G2. That's going to be a vector. If you integrate that, like what happens here, integrate that. It means that you're going to integrate term-wise, right? So that's integration alpha G1 plus beta G2, as well as the integration of gamma G1 plus delta of the G2, just integrate term-wise. Is that good for everybody? Okay, so that's the 3 remarks about how to apply this formula to your exams. Okay, so this is going to be a very important formula. And remember, you have to keep it in mind. You won't be provided with this formula on your exam, but you have to keep it. Is that good for everybody? Okay, so remember x of t is cosine tc plus cosine t cosine inverse of tgt, where before the cosine inverse tgt, there is an integral. So you are not able to cancel the cosine t with the cosine inverse of t. Is that good for everybody? Okay, so this is going to be a very important formula that we're going to see some exercises, how we're going to practice. Okay, so let's look at this formula. Okay, so this example, if A is 2 minus 3, 1, and minus 2, GT is 3 ET, cosine T is the fundamental matrix, X prime is equal to A log X, right? So all these data are given. Can you find a general solution of the non-homogeneous system, which is X prime is AX plus G? Okay, so this one is just applying the formula. So let's say X prime is equal to AX of T plus G of T. And on an exam, you have to kind of tell me that the formula in general, the general solution is the fundamental matrix multiplied by constant, right? So remember, it is the fundamental matrix up to the integral of the cosine inverse of T multiplied by G of T dt. That's going to be the formula. Now, therefore, the rest of the story is to just apply this formula, right? So, and how do we find cosine T? Well, remember, cosine T is a solution of the non-homogeneous, the corresponding homogeneous equation, right? So, but do we have to solve it? We don't, because the cosine T is already given in this problem. It's 3e power t and e power t, right? So 3e power t as well as e power t, and then it's e power minus t and e power minus t. So that's going to be the cosine t. And therefore, you just need the g of t. The right-hand side is also already given 3e power t and e power t, right? So that's 3e power t and e power t. So that's going to be the solution. Therefore, you can just apply this formula, right? So in order to apply this formula, so we can say that this is 3 times e power t, right? So e power minus t and e power minus t. Multiplied by the constant c is c1 and c2, right? So plus the cosine of t is 3 times e power minus t, and e power minus t. So that's going to be cosine t. And then the integral of the cosine inverse of t, right? So what is the cosine inverse of t? So that's going to be the case, right? So remember, cosine inverse of t is 1 over the determinant of cosine, and then you're going to switch the diagonal. So e power minus t, 3 times e power t, switch diagonal. You're going to take a negative on the off diagonal, okay? So you're going to take a negative on the off diagonal. So what is the determinant? Well, here is 3 e power minus t is 3 minus 1, so that's 2. So therefore, determinant is 1 over 2 of e power minus t minus e power minus t and minus e power t, right? So, and then 3 times e power t. So that's going to be the case. So therefore, this inverse matrix is just the e power minus t, minus e power minus t, and minus e power t, and 3 times e power t. So that's going to be this matrix. Then you're going to multiply by 3 times e power t as well as e power t dt. So that's going to be what you're going to calculate. So the rest of the story is just a calculation. You first have to calculate this product. Is a good family? Okay, so first have to calculate this product. So therefore, you are going to kind of end up with the following, right? So let's say this is just calculating the cosine inverse of t. Okay, so let me put it in the next page. Okay, so let me put it in the next page just to show that what we have been calculating here. Okay, so let me put it in the next page, and I will continue with this calculation. Okay, so let's kind of put it here, right? So that's going to be your fundamental, your general solution. So let's say this is x of t is equal to this object. Now you have to calculate this product. So that's 3 times et e power minus t, e power t, e power minus t, multiplied by c1 and c2, plus this matrix 3 times e power t, e power minus t, e power t, e power minus t, and then there is a 1/2. You can pull it out. Now the integral is the matrix product. So this one is 3 times minus the 1. So that's the product is 2. Right? So here is e power t, 3 e power t. So it's a minus 3 e power 2t plus 3 e power of 2t. Is a good family, right? So that's therefore this is going to be 0. Okay, so indeed we're just integrating a vector 2 and 0 with respect to dt. So what will be that integral? Well, this integral is going to be just, okay, so it's just the same thing as the integral of 2 dt and the integral of 0 dt. Is a good family. So that's going to be, just pick one antiderivative. That's 2t, and let's say the integral 0 dt is going to be just equal to 0. Okay, so you're just going to pick one candidate of that equation. Is that good, everybody? Okay, so that's going to be what you're going to integrate, how you're going to integrate a vector, right? So you're going to how you integrate a vector, right? So now as long as you have this, okay, so that's as long as you have this, you can kind of put everything back into this equation, right? So that's 2t. So therefore, if you continue doing this, you're going to have 3 times e power t, e power minus t, e power t, e power minus t, multiplied by the vectors c1 and c2, and then plus 1/2 of 3 times e power t, e power minus t, e power t, e power minus t, multiplied by 2t and 0. Is a good family, right? So, and then you can observe that this 1/2 cancels with this 2. So you have this, right? So, and then that's going to give you the solution just by standard matrix product. So that's 3c1 e power t plus c2 e power minus t plus 3 times t e power t, and there's 0. And then the second part is going to be c1 e power t plus c2 e power minus t, right? Plus, let's say t power of t. Is that good, family? Okay, so that's going to kind of give you the final solution, right? So that's going to give you the final solution, and this final solution is nothing but let's say a general solution. So that's a general solution to the non-homogeneous problem. Okay, so that's the general solution to the non-homogeneous problem that you must keep in mind. Is that good, family? Okay, so that's kind of apply one of these formulas. Okay, so now let's look at one more example. Okay, so can you use the method of variation of parameters and you solve this system? Okay, so I'm going to solve the system which is going to be like this. So dx over dt, right? So dx over dt is a minus y plus a secant. Okay, so minus y plus secant of t, right? So and then we're going to say dy over dt is equal to x. Okay, so dy over dt is equal to x. So this is a system of equations that's a non-homogeneous system, but it is written, right? So in a component form. So therefore, you have to kind of let the x of t. So let me set x of t is equal to xt and yt, right? So there are two components, right? So xt and yt. you must recognize that this vector x is different from the component x. This is just a component, and this is a vector. So how do we write this equation in such a system? Well, you can say that d by dt of xy is equal to a matrix multiplied by xy. So what will be that matrix? Well, you have minus y, so you have minus 1 here, you have 1 here, you have 0 and 0. So you're going to have this. And then plus the non-homogeneous term is going to be second of t as well as, okay, so second of t as well as 0. So that's going to be the scenario. Is that good, family? Okay, so once you have this, okay, so once you have this, you can see that the matrix A is equal to 0, minus 1, and 1, and 0, and the vector G, T is equal to secant of T as well as 0. Is that good, family? Okay, so once you have this, you have to kind of solve the system, right? So if you want to solve the system, then it's not easy story, right? So easy story, but here it says that the problem is not finished, but it says that the general solution to the associated homogeneous system. What is associated homogeneous system? It means you're going to remove the secant of t, and therefore you're going to end up with just a complementary equation. Therefore, if they say that the general solution of the associated homogeneous system is a linear combination of these two solutions, it means that these two solutions are fundamental solutions. Is that good, everybody? Okay, so you must kind of interpret this notion here that this is the first fundamental solution and this one is the second fundamental solution. Now, if you know the both of the fundamental solutions, you, as we said, you put them as column vectors in a row, you are going to end up with the fundamental matrix. Is that good, everybody? Okay, so that means you can end up with the fundamental matrix. Cos of t is the fundamental matrix, but it is actually already given is cosine, sine, and minus sine and cosine. So that's going to be cosine of t and sine of t and minus sine of t as well as the cosine of t. Okay, so that's going to be the scenario. So that's going to be the fundamental matrix. You don't really have to calculate. And that's actually what actually happens most of the time on your exams. They're not going to ask you calculate anything, but you can kind of interpret this fundamental matrix just from the given information. Okay, so once you have the fundamental matrix, my suggestion is to calculate the inverse matrix first, right? So the inverse matrix, remember, is the determinant. Here the determinant is equal to 1. So 1 over the 1, and then you switch the diagonal, it's cosine t, you negative on the off diagonal, sine t, and minus the sine t. So that's going to be like cosine t and sine t, and minus the sine t as well as the cosine t. So you're going to have cosine inverse of t. Is that good, family? Okay, so now once you have the both the cosine and cosine inverse, you can just apply our formula. So the formula says that the general solution is going to be equal to cosine of t multiplied by the vector plus cosine of t multiplied by the integration cosine inverse of t multiplied by gt dt. Is that good, family? Okay, so you apply this formula, you are going to see that cosine of t is equal to cosinesis of t minus the sine of t, right? So minus the sine of t as well as the sine of t, cosine of t, and then multiply by the vector c1, c2, plus the same matrix, the cosine t minus the sine t, right? So let's say the sine t as well as the cosine t, and then the integral of cosine inverse. So the cosine inverse already calculated. That's why I suggest you to calculate it before you proceed. So that's cosine t minus sine t minus sine t cosine t. Okay, so that's cosine t and sine t minus the sine t and the cosinesis of t multiplied by the g of t. Okay, so the g of t is secant t and 0. So secant t, remember, secant is 1 over cosine, and that's a 0 of the dt. So that's the equation. Okay, so that's the solution. And the rest of the story is to perform this matrix vector product first. Once you perform the matrix vector product, you integrate. Okay, so that's going to kind of tell you, right? So let's first do this, right? So that means the integration is about to have 1. Okay, so and then a minus sine over cosine plus 0. So that's going to be minus of the tangent of t, right? So you're going to integrate this object dt. Is that good for everybody? Okay, so and if you integrate this object, it's the same thing as the integration inside the integral, right? So that's going to be 1 dt and the integral of tangent. And if you integrate 1, you're going to just end up with t. Okay, so we're not worried about those constants and the antiderivative because they're not going to kind of hurt us, right? So what is the integral of tangent of t? Well, if you are familiar with calculus, integral of tangent is equal to logarithm of cosinuses of t in absolute value, right? So in terms of minus, right? So that's going to be kind of what happened here is that the integral of tangent with a minus sign can be calculated. Okay, so here I will skip this calculation, but it is equal to ln multiplied by cosinuses of t if you perform this integral. So that means you can finally have the answer is minus sine of t multiplied by the sine t and cosine t multiplied by c1 and c2 plus the product of this cosine t and minus sine t and sine t as well as cosine t multiplied by this. So therefore, you can kind of finish the story by doing a matrix vector product yourself and end up with the answer. Okay, so I will leave this as a homework exercise to perform it. But finally, you will end up with the answer. Okay, so the answer is going to be something like this. Okay, so the answer is going to be something like this. Okay, so I will take this answer. Okay, so that will be what you finally can calculate. Okay, so that will be what you finally can calculate. Would be something like this. Okay, so that's kind of after all these calculations, you're going to end up with a formula like this. Is that good for everybody? Okay, so this is how you solve a non-homogeneous system using our standard formula. Okay, so remember after this class, this formula is going to be crucial for the rest of your exams. Okay, so you're going to kind of see it in the final exam that they are going to you have to kind of interpret the information of the fundamental matrix psi of t, and you have to perform psi inverse multiplied by the right hand side, integrate, and then multiply by cosine t and add it by the complementary solution to reach a general solution. So this is a very important lecture, and I hope you will be able to grasp it. And in particular, this formula is supposed that you must keep it in mind. Okay, so that's going to be kind of very important for this lecture. And this is all I want to say for today's lecture. Let's stop here and we'll continue our discussion in the next lecture. Okay, so see you in the next lecture.